Good morning, everybody. How are you? Ciprian speaking.
Good morning, Ciprian. All good here, thank you.
Good. Let's see. We have today 6 presentation. So the first, before we start, we have Peter. Yes, he's
hello.
Here. Peter, actually.
Yeah.
Okay. And then I think Marian NECULA will be the next. Then Daniel Wagner-Schuster. Then Stefan, it's here also. Yeah, it's Stefan FLECK, okay. And Bogdan OANCEA. And also Luis Sanguiayo, yeah. Luis, you will present the last, the geolocation of mobile devices?
Yeah.
Yeah, okay, good.
Okay, so I think we are complete from the presenter side. Let's just wait until 10, then we will start.
Yeah, of course. I want to be only sure to that we have all the presenter here online and with coffee drinked already. Thank you.
Good morning, everyone, to the last day of this year's uRos 2020. Just a quick reminder, if colleagues ask you about live streaming on other platforms, unfortunately, we don't have that today, so please advise them to join us here in WebEx. if you are asked. Okay, with this short note, I directly hand over to Ciprian, who will share the scientific session.
Thank you, Alex. So today we have a very nice session. Also today we have a very nice session about R for web and other data. So will be 6 presentations. Some of the presentation will include some results from some MEIßNER projects, but all the presentations are very interesting, and we're looking forward to see that presentation. So let's start this very interesting session with Peter MEIßNER. He will present using R for web data collection at scale. He's coming from Virtual 7 company from Germany. So Peter, you have the floor, and good luck. Thank you.
Thank you. Hello, everyone. You see my slides?
Very well, thank you. We see you and we hear you very well.
Okay, perfect. So, yeah, using R for web data collection at scale. So how to make R something which can operate at web scale. So this is to talk about. About me, I'm a social scientist by training. I'm kind of an IT guy by design. I'm R textbook author, long-time R user, R package author, and I'm also a consultant data scientist at Virtual 7. This talk is kind of 2 things. One thing is it's a customer story about a project with a public sector client about scaling R. And it's also the origin story of the new R package, Kafkaesque, which you can use to interact with message queue called. So to get started, let's set the theme. We got into contact with a public sector agent, and they are quite knowledgeable about data analytics and data quality. They have a lot of fresh ideas, but what they were lacking is a little bit like capabilities and building and scaling software systems. So it wasn't their core skill. So this was where we came in. And the mission was to build a software system and scale a system that would collect specific data from the internet. So basically what the system should do is do web searches, get back some results like web pages, and then go to all of those web pages and not just download them because they are probably dynamic pages, but render them in some browser, and later on do some data extraction. So you have kind of 3 tasks: some searching, some rendering, and some data extraction. Now, all this while using R. So this, yeah, R is not particularly known for its speed. Also, it can be quite fast, and it's not known for scalability, but it's a very elegant language. It's a very robust language. And if you're dealing with data, R comes with all the data management you need built in, which is really, really nice. And for the customer, it was a well-known quantity. So we built our system around R. So to get an idea about the scaling involved, so the task was to do like 500,000 of searches, and which then would result in 7 million page renderings, which then would result in 7 million data extractions. And this should be done in some feasible time. like think maybe 1 month or something. But if you look at the different tasks, then searches, they are quite fast, so you can get a lot of those done within a minute. And also data extraction was not a big issue, but page renderings took around about 20 seconds per page, because sometimes you can't be sure when the page is actually done rendering all the JavaScript. So if you do the numbers, then you see that searches could be done in 1.5 hours and data extraction 16 days. Maybe you can tweak performance there a little bit. But the big problem is page renderings, right? And the thing is, this is not about R, because the page renderings are not done in R, but in a headless browser, and this is kind of a fixed setting. So what to do? We kind of have to scale the system, right? And scaling is almost always some variation of the theme of divide and conquer, right? You split your task, your procedures, your code into smaller chunks, and then you parallelize, and thus you conquer the problem. There are basically 2 approaches to scaling. One is kind of a push approach, right? You push work into the parallel into the system. And this is basically, I think, the first go-to, right? You have a single main application, and there you maybe have a loop, and you parallelize the loop, for example, with the future package in R. And so this is easy to get started, and you don't need much extra software, and you can maybe take some shortcuts to make the things more efficient. On the downside, you have a single point of failure, which is not very nice. So if your main application breaks for some reason, and when we're talking about web data and interacting with web pages, there's always the possibility that something breaks, or if things run very long, like for days. And also, like the coordination of distributing the work might become a bottleneck in its own right, which might be a problem. And the other thing is, like, you have to know in advance how the topology of your compute looks right? So if you have your main application, you distribute work, then you have to know, like, how big is the server? Are there any other servers which I can use? Can I connect over the network and stuff like that? How much memory do I have? Another approach, and the approach we in the end took, is more like a pull approach, right? You don't have a single main application, but you split the application in multiple parts, and the main idea is that you have a lot of dumb workers which just start up, ask for work, do a task, report back, and you can scale those up and down while the system is running, and it's very robust. You can easily distribute it. So this is highly scalable across computers, across networks, across clusters. But it needs more planning upfront and some extra bookkeeping about who does what, when, and how. So this is much more scalable in the end. So we use the pull approach, and so one thing we also had to do was kind of think, like, where could you parallelize, right? So you have your task, and so when you have something like a task list, you have a search, then you have some renders, then you have some extract, then you go to the next search, and so on and so on. So you have a series of things to do, and you can break this up and say, okay, I mean, all those searches are completely independent of each other. Maybe the searches and the renderings depend on each other, but the others, they are completely independent. So I can trivial parallelize those, and even within those small chains, I can make something asynchronous, right? So I don't have to do all of them in this order, but I can choose in which order maybe to do it. Now, how does this look like? So when you build a system like that, you end up with some weird diagram with some servers here, and then you have some workers here, and a task queue, and a schedule, and a relation database, and a storage device. So starting from the idea that we have workers and possibly a lot of them, here those workers, they basically don't do much. They just know how to execute tasks, and they know how to get a new task from some queue. Right. So when they know how to get some task from queue, what you need is a task queue, right? To store the task and to be able to say, okay, to make sure that only one worker does one task, right? So not multiple workers try to do the same task. You need some coordination there. So you have a task queue, and you're good. Then, of course, you want to store the web pages and the data extracted. So you need some data storage. And it would be nice to have something like, for example, some bookkeeping, like how long took the task and what's the status of the task, had an error or was it done, and what are maybe some relationships between the tasks. So which page rendering belongs to which search task and stuff like that. And then you can choose technologies, so specific technologies to put into your workers, right? We choose R to put in to use for our workers, and we choose Kafka for our message queue, and PostgreSQL for the bookkeeping, and also PostgreSQL to actually store the web pages, and some simple cron scripts to do some daily maintenance or to automatically scale up or down workers. So question is, did it work? Like, how good did it scale? Because this was the thing we set out to do. We had those 7 million page renderings, which took quite some 4.5 years. And with this architecture, with a simple desktop PC with some CPUs and 32 GB of RAM and the quite standard network connection, you could do the tasks within 55 days. So, I mean, this could be a big laptop, right? Which is quite good. So this is a lot of kind of bang for your buck. But this is like a scalable system. So what we, for example, tried out to kind of prove that the system really scales is we put it into the cloud on a larger EC2 instance on AWS, and then we got results like we could scale those 4.5 years down to only 10 days, and basically, and this is something you get for 4,000 euros per month, but you could also kind of buy a server on your own this size. But in the end, the sky is the limit. So this is not like where the scaling ends. You could make it even do more work, right? Because you could use more servers. Yeah. So this was done, right? So task completed, and kind of a bonus of this project was that we heavily relied on Kafka as a message queue or task queue, and there was no working Kafka bindings for R. So there was a package, but it wasn't working anymore with new Kafka versions. So we started to use this package, redesign it, and use it within the project. We gathered a lot of experience with this, and what we did in kind of the last half year is we took all our experience and we put it into a new package, which is more streamlined, kind of more robust, and which I think has quite nice APIs. So you can put, for example, data frames into your message queue, so the aim was to make it kind of a user-friendly big data for mere mortals, right? For technical R users, but not for like super programmers or something like that. Yeah, it's free. It's on GitHub. It's not yet on CRAN, so there. I still have to think about it. I tried to get it onto CRAN, but the package is larger than 5 megabytes, and CRAN does not like this too much, and I have to think about how to solve this. But I think it will be at the start of next year. This will also be available on CRAN. So thanks. I hope I'm in time.
Yeah, thank you, Peter. Actually, you are in time because I didn't announce that we should keep in 15 minutes, but very good. So I will kindly ask all the presenters from today that presentation should be around 13 minutes with, let's say, 2 minutes for Q&A. Okay, Peter. Very nice work, and we know that is very important for big projects when you work with data from web, that you need a lot of hardware resources in order to manipulate the data and do the analysis with good results. So I think it's very nice work, and very important also for our National Institute of Statistics, because we work more and more with web data. So thank you very much for your presentation, and if there are somebody who wants to ask, please use the Q&A section in the WebEx platform. Even though at this moment there are no questions, you can address the question.
Question by Olaf.
Yeah. I didn't see. Yeah, it is a question. Okay, interesting. So from Olaf, interesting. Could you maybe say something about the aim of the search and scrape? What kind of data was collected in this volume? What kind of statistics were produced?
Yeah, no. I'm sorry. I love to get more into details, but I'm kind of not allowed to disclose what was the data collected, who was the customer. So this is like
at least volume, maybe. Maybe you can say the volume, how large the data are, maybe. data
so
which you test.
Okay, so the data
From
collected. So this was this, right? So this was
okay.
the aim to do 500,000 searches, 7 million page renderings, kind of within a month. And in the end, this is like if you do it monthly, it sums up to something like 300 gigabytes of data per month. And then you have to decide if you replace or if you do it over and over again for the same pages, if you replace the pages or you collect them all and do some history. So then you have like 300 gigabyte or 300 gigabyte per month.
Okay, per month, but you collected all along the month, so not all in one day. You collected and then you run, let's say, some task over this amount of data. Yes.
We did it all like at the same time. So so I mean we did not use it for actual data extraction. So the customer will do this, right? So we were only for the scaling part, building the system. But the idea is to do a certain amount of searches per day, right? And then directly after this, so when the first search results come in, then the first page renderings will start also, right? Because searchers will produce new page rendering tasks, they are in the queue, and then the worker pick up those tasks and they will do it directly. It's not like collecting searches for 1 week, then doing like page renderings for a month, and then doing the data extraction, but doing it repeatedly as fast as tasks come in. So it's more like a stream architecture than kind of a batch architecture. But you can collect in the end. You can collect the data from the data extraction from the web pages in an ordinary database table or tables.
Okay, good. Thank you. So there is one more questions, but I kindly ask you to answer to the Q&A section because we have run out of time now. In conclusion, we hope that your work will be on CRAN or any other open source platform in order to be used also by official statistics, because in this moment you are the only one beneficiary, and we wish you good luck to make it open source. Thank you.
Yeah, thank you.
Good. Thank you, Peter. We'll go to the next presentation, which is R for web scraping, online job adverts, and computing potential indicators. And the presenter will be Marian NECULA from Institute of Statistics Romania, and also is affiliated at Bucharest University of Economic Studies in Romania. So, Marian, if you are ready, you can share your screen. Please proceed.
Yes, thank you. Can you see my screen?
Yeah, we have only to make the full screen maybe, or leave it like that. I don't know. How do you prefer?
I'll leave it like that.
Okay.
I need to step into two PDF documents.
Good.
Okay. Good morning to everyone. My name is Marian NECULA. I work for the Romanian National Institute of Statistics, and I'm a PhD student in statistics at the Bucharest University of Economic Studies of Bucharest. The work presented today was done for the ESSnet on Big Data 2 grant in work package B. online job advertisements or online job vacancies, where the goal was to estimate the number of job vacancies at the level country or at a more granular level using online job advertisements. The data was collected by CDFOP and two other commercial companies, I believe Tabula X, and the last one, I don't remember, two companies from Italy. They collected about 64 million online job advertisements, about 64 million observations from 28 countries in about a year or so. Inside this project, there are many little projects developed by each country, depending on their interest. Also, I'd like to mention that the work done in this project will be continued inside what I think is the future of official statistics, the next project of Eurostat called Web Intelligence Network and Web Intelligence Hub, which is the network for all the official statistics institutes or offices inside the Eurostat, where they put together, or they try to put together, a pipeline for production which can be used by all countries. This, I think, will be a great unification or a potential unification of the system, the starting point. So inside this project, we computed, based on the data provided by CDFOP, a number of indicators which can be used to as descriptive statistics, which can be used to assess the quality of the data or the collection process, or as proxy variables inside different types of models. So we computed, this document was built on CDFOP data. We used R and R Studio. Also, I'd like to mention that the infrastructure, it's hosted on AWAS cloud computing servers. And we had some tools to interact with the cloud computing servers, like Sparkler, dplyr, and ggplot we use here, but there are other type of tools or R packages which can be used to interact with the databases hosted there and with the computing resources. The results contain a number of graphs related to the number of online job ads, and a breakdown by different type of categories of variables, like the data collection period, the economic sector, the education level, ESCO level 1, and experience requirements for each job advertised. It was generally observed that the collection process is not uniformly applied to all target countries, and for a better representation of the results, some graphs are plotted against logged count values. And the main findings were that the collection process seems uneven between countries and periods. Some countries have a significant number of ads were collected from foreign websites. I like to mention that the collection process for each country was done using websites in the country's own language. For example, in Netherlands was done for websites in Dutch. For Romania was done for websites in Romanian, but also from international website aggregators for online job vacancies, mainly I think in English was the primary language, which targeted jobs in Romania. The job ads per category sector are in line with the economical reality, as described by the three-sector model. Job ads per experience require suggest that up to 1 year of experience is overrepresented in the total number of job ads. Job ads per ESCO level show that the job ads addressed to professional technician and associated professionals are overrepresented. This seems logical, taking into consideration point C. Also, in relation to the case study, Romania websites as data source, that generally follows the real economic trends for migrating workforce, except for information regarding some countries. Romania is confronted with a migrational problem. A lot of the population has moved to other EU countries after 2007, mainly Spain and Italy. For which the well-known high provision of Romanian workforce is clearly underrepresented by ads. Possible explanation for this is that for these countries, the supply of workforce is directed towards agriculture and manufacturing, also correlated with the three-sector model by Eurostat. So these are the graphs. They are very uneven. What we were confronted in this work done inside the work package B online job vacancies for ESSnet on big data tool was that the process, the collection process, and the pre-processing process done by CDFO and other parties involved, other third parties besides the teams involved from Eurostat and national statistical offices, was not very transparent. And they didn't have explanations why for some countries they are overrepresented. But one naive explanation could be the size of the economy for these countries and the population. In this case, we expect that Germany, Deutschland, should be overrepresented like France or the UK. For within the reference period, for example, this is the graph. These are the graphs for the collection process. The process is not uniform. There are different periods where they collected data and other periods where they didn't collect much data. Here to better represent the data, we took a logarithm of the counts, and we can see that in magnitude, some countries, for some countries, data was collected at a far greater pace than other countries. These are by source country, where the website is presented. The log ads for each country. This is for, I think, Austria. This is for Belgium. We computed these type of indicators for each country in part. For example,
Marian,
yes.
Please conclude in 2 minutes. Thank you.
Okay, thank you. So the main findings are that the collection process is uneven. Some type of jobs are overrepresented by comparing with the data from the surveys done inside our national institute or done by other countries. They reported the same problem, that some type of jobs are underrepresented or are missing from from this type of data. This work should be extended in the next phase inside the Web Intelligence Network and Web Intelligence Hub, which will be a great opportunity for official statistics. Okay, thank you. If you have questions, please ask them.
Yeah, thank you, Marian. It's a good effort to have this data with so many countries. There are a lot of differences between the countries, also from the point of view of representation of the economic activity and the occupation on online job adverts, because not all the countries have the same behavior related on the job adverts. Yeah, we hope that we will continue this work in the next project. So at this moment there are no questions. I remember you that you can address the question at any times. So I have a question. Okay, thanks for presentation. Question from Martin. How did you compile the list of job advertisement website? Which to scrape? Did you use the country local websites?
Yeah, local websites were the main were the pivot variable used to compile these statistics.
Okay, thank you, Marian. So thank you for your presentation.
Local websites identified by the I don't know, the last part of a URL domain, the domain of the website.
Yeah, specific for each country. Yeah. Good.
Thank you.
Thank you very much.
Ciprian, you are muted.
Thank you, Alex. Okay, so we'll pass now to the next presenter, Daniel Wagner-Schuster from Joanneum Research, Austria, with the presentation between R and Excel, the ETER data validation quality process. So, Daniel, the floor is yours, please. Thank you. And remember, 13 minutes, please. Okay, we see your presentation.
Okay.
Okay, we see a presentation. We didn't hear you very well. Daniel, we didn't hear you very well. Maybe if you close your webcam to stop only the video and to remain only with the presentation, maybe it will increase the quality for the.
Okay, is it better now? Can you hear me now?
So.
Yeah.
Yes.
Okay.
Thank
very
you.
good. Thank you. I thought the project would be interesting because on one hand, we use R extensively within the project for a lot of tasks. On the other hand, we get the data from national statistical authorities, and we are constantly in interaction with statistical authorities, with other groups of users and managers in the project. So first, a short overview on the project. It's called the European Tertiary Education Register. Within the project, we collect data on the level of higher education institutions. This is quite unique because you can find data on the level of institutions, but not at this large scale. So you can find some data, but not in this detail on the one hand. And on the other hand, you can find data for some countries, but not for whole Europe. And the project actually ended last year after the submission for this conference, actually. But there will be a new tender. Maybe we can continue to do it another 3 years. At the moment, we have data for 37 countries in Europe, about 3,000 institutions per year. And we currently have data for 6 academic years and about 17,000 observations and a bit more than 600 variables. So if you are interested in higher education data on the institutional level, you can have a look at etterproject.com. So we national authorities and managers are from approach team from side with data collection. We needed to find a way to use different tools in this process to solve the challenges and also interact with all these groups which are using the results. Collection itself. Can import so we step back to the rows more.
Daniel, you can hear us? Can you hear me?
Yeah,
we didn't hear you. Yeah, but we didn't hear you very well. It's a very strange sound. Maybe you have some trouble with the bandwidth of the internet. I don't know exactly.
Okay.
So my proposal is that maybe it's better to interrupt your presentation now, and maybe we'll come back to you after the next presentation, if you are not if you are okay with this proposal.
No, that's okay for me. Yeah.
Yeah. Or let's try And now I hear you quite well. Let's wait 1 more minute, please. No, it's not okay. Yeah, it's not okay. Something, but I don't know because I see you very well and also the presentation.
Maybe you can switch audio and try to use one of the phone numbers. There's also an Austrian toll-free phone number where you can call in and connect your phone audio to the WebEx session. And we move to the next presentation, and in the meantime you could switch audio and then we come back.
Yeah, and maybe if you send us the presentation, we can share the screen with your presentation, if you consider. It's okay? I think yes. I think now the screen it's freezing. So we will pass to the next presentation and we will come back to you, Daniel. Okay, thank you. Don't worry. So the next presentation is a web service for processing GPS data from mobile phones. And the presenter is Stefan FLECK from Statistics Austria. So Stefan, if you hear us, if you are ready, please share your screen. Okay, I see your presentation. Let's hear you.
Okay.
Also. Okay, thank you.
Okay,
please
thank
remember
you.
13 minutes, yes? Thank you.
I will try to stick to the time. So
Good,
my name is Stefan from Statistics Austria. I work at the transport unit. And in 2019, we developed a mobile app for the road freight transport survey as an alternative to the traditional questionnaire. The app can automatically fill in some of the data that we need by analyzing the geolocations recorded by the mobile device. And this leaves fewer questions for the respondents to answer and saves them valuable time. In this talk, I want to talk about how and why we implemented the processing of the location data in R and set up a web service with Plumber to make this functionality available to the backend of the. I will start by discussing how we solved the problem of deriving travel distance from position data. Then I will explain why we decided to choose a web service for deploying our code and what the advantages are. And then I will show you the actual architecture of the whole system and some code examples. And I will close with a small conclusion and reference some additional reading on the topic. This talk is aimed at people who have not used Plumber before, and I only have 30 minutes of time. So I can only skim the topics, but I'm happy to answer more detailed questions afterwards. So first on the GIS part of the whole project. For the statistics we publish, we need to know the total distance of each journey of trucks and potentially all transitioned countries and border crossings. This can be derived from location data as provided by mobile devices, but it is not completely straightforward. The mobile app records the global position of the device as latitude and longitude, and usually we get one such position every few seconds, depending on the device. But it's not always that clear cut. As you can see on the maps, for example, on the top map here, there are some nasty outliers in the data that we have to remove. And as you see down there, there can also be significant gaps in the data that we have to somehow impute. Those gaps can be especially large for some phone models that have aggressive power saving settings. And sometimes it might happen that we only get a few points to at the beginning and the end of the journey. And to solve this problem, we came up with a fairly simple algorithm. I only want to explain for a short for a short bit. The idea was first we remove all points where the position accuracy as reported by the mobile phone is really bad. So less than 20 meters is not really usable for us. Then we also clean up points where the reported speed of the vehicle is less than 7 kilometers per hour, because we assume those are rest breaks where the driver forgot to switch off his app or something like this. And we found that by removing points where the reported speed is faster than 130 kilometers per hour, that's a very good strategy to remove outliers. So after we clean the points, we connect the points that are really close together just to straight lines because it's accurate enough. And if we have huge gaps, we rely on an external routing service to route all points that are more than 50 meters apart. And I just ran through it very quickly now, but you have to trust me that this produces very good results for the journeys that we receive. And one could think, now that we developed the algorithm, our project is finished, but it is not, it's just beginning now. Because now we think about how do we implement this model that we came up with in production. The problem that we face is a new journey can be submitted at any time of the day and needs to be processed within a few minutes. So the simple solution, just execute the script whenever we receive a new journey, is not really feasible for our case. Something a bit smarter that would actually probably work is design an R script that is callable from the command line, deploy it on the machine where the backend of the mobile app runs, and then the backend could always call the script whenever it needs to process a journey. But this has several very grave disadvantages. First, it pushes the responsibility for maintaining the R environment to the same team that develops the mobile app, which in our case, rather than us who are the developers of the R code. And it would also make the whole setup of the backend more complicated and introduce additional failure points. In addition, this also means that the app would always need to be, that the app team would always need to be involved if we wanted to make modifications into our geoprocessing R program. So the best solution would be turning our code into a standalone web service. And this has several very clear advantages. By defining an API, so an application program interface, a way for programs to communicate with each other, by defining such an API, we can define and formalize very clear boundaries between two components of a system. In our case, this corresponds also to the border between teams. For example, the IT unit maintains the mobile app and its backend, and we maintain the geoprocessing service. And there's like a very clear interface between both of our teams now. For communication with web APIs, we use HTTP, the protocol that powers the whole World Wide Web. So it's a very well standardized, very well-known protocol, and practically all programming languages can use HTTP APIs without problems. So we're not limited to any technology. Also, since we run the service on a dedicated machine, we have total control over the R execution environment. So if the local infrastructure allows it, we could freely decide on which R version, which operating system, which R packages, and which system libraries we wanted to use. So this is really nice for isolated services. An API like this makes it also very easy to deploy different versions of the same service. So for example, we can have development, testing, and production stages without any additional hassle for us. And the service is reusable for other projects. So for example, what I did, I made a small side app, like a small Shiny app that also uses the same API to make it possible for our staff to review the routes as they come in. And for our project, but this is really limited to our project, we had the special advantages that we could reuse some existing R code for the geoprocessing service. I also want to show you a bit, like, this is how the architecture of the whole system is. We have the mobile app here. The mobile app communicates with the backend over a web API. And down here, we have the routing service from which we use to fill in the gaps in the data that I showed you before. This one also exposes a web API. So it's completely natural and logical that we also choose to use a web API to expose our geoprocessing service in the system. An architecture like this also has the great advantage that we can replace every component of the system easily without any problems, as long as we keep the API stable. For example, if we decide we want to switch from R to Python, we can just replace the geoprocessing service by a different one seamlessly without any problems for other parts of the system. The same is true for the backend, and we can also use a different routing service without problems. It's all very neat from an organizational point of view. So how does the actual code look? I only very reduced example here, but this is how the server-side code of a typical plumber function works. We define a normal R function that we augment with special comments that you might know from Roxygen if you're a package developer, or you might know the principle from Roxygen. It's different comments than the Roxygen comments, obviously. So the most important part of this special comment, well, that was the wrong. The most important part of the special comment is this line here. That's the so-called endpoint. That's the URL that we use to access this function. And the ID here is something that will be passed into our function as an ID that we can, for example, use to select something from a database, and then process the data and return a return object to the sender of the request. There's also, Plumber also uses this special request object that it passes into a function that you can use, for example, in this case, for error handling to return proper HTTP response codes in case you encounter an error on the way. If you want to learn more about HTTP status codes, I don't really have time to explain that. I put a small link on the bottom of the slide. Similarly, the client code looks even simpler. The example here is now an R client that uses the HTTR package to send an HTTP request, but you can also use curl from the command line, or any library, any programming language will have a library for this to receive, to send HTTP requests, receive responses, and pass the content. For example, here we wanted the summary of the route 12345, and we get back the distance in Austria, the distance in a foreign country, which is none because it is Vienna to Klagenfurt, and HTTP is smart enough to pass the data already for us if it's in the proper format. In this case, the response is actually in JSON, but HTTR does all the work for us and passes it to an R object. An API does not only have one endpoint, it has several endpoints. So this is a partial overview over the endpoints we expose in our geoprocessing service API. You can also note, I just talked about GET requests before. There are also other requests, for example, a delete request that you can use to delete data. In this case, I used it to invalidate an internal cache inside the API. And this is something that is actually very important to understand. If you implement an API, you really should know what are the semantics of the HTTP methods and implement them appropriately. Otherwise, it's really easy to come up with an API that works, but is a total mess and kind of hard for other people to use. So please,
Stefan, please, 2 minutes.
Okay, that's fine.
Thank you.
Also it's already my second last slide. Yeah. So all that I actually wanted to say, you can refer to this link to You can refer to this link to see all the HTTP methods that are available and their semantics. So now the conclusion. In conclusion, we saw HTTP APIs are a very powerful tool for patching applications together and providing services with well-behaved APIs is in turn a great way for different teams to collaborate together on complex IT projects, independent of the technology that they're using. The Plumber package makes it very easy to create HTTP APIs for your project, and the HTTR package makes it very easy to access such APIs from R. So, like in a one-sentence conclusion, use APIs. To give you some additional motivation, in 2002, the founder of Amazon, Jeff Bezos, wrote a very famous email to his employees where he said, teams are only allowed to expose their work to other teams through services with well-defined APIs, and everyone who doesn't comply with this rule gets fired. And today, Amazon is the most valuable company in the world, so apparently using APIs is something that seems to work pretty well, at least for team collaboration. Thank you for your attention. That was my talk. Here is some future infos on the topic.
Thank you, Stefan. So we have one questions, but before these questions, I appreciate your work, and we use in Romania also this package very well. It's a very nice software. So a question from Martin Liberts. Thanks for your presentation. Did you provide mobile devices on truck drivers?
No, they have to use their own device.
Okay. How? Yeah, please.
Yeah, it was just simply not feasible for us to provide mobile phones to all the drivers. And since it's only optional for them, we also have other possibilities to report. Yeah.
And how do you manage the security of the Plumber API?
So
how do you control who can execute the API?
Okay, so that's not such a huge problem, because all the security stuff happens between the mobile phone and the backend of the mobile phone, which is an application that runs already in Statistics Austria. And the Plumber API is only available inside Statistics Austria, so it's not exposed to the internet, because we have this backend in between, and the backend uses authentication between the same portal software that we use for all of the stuff of Statistics Austria that's exposed to the outside.
Okay, thank you. And one more question. This question is from Jan. Do you think that it is possible to plan the route, including the vertical movement? And like an example, multi-stage buildings?
Sorry, what?
Yeah. Do you think that it's possible to plan the route, including the vertical movement?
No. So, I mean, GPS by definition GPS only works on the outside, more or less. As far as I know, there are studies for navigation systems inside of buildings, but that's like a kind of a different topic. And I mean, for our case, that's something that's not really relevant, because we actually want to filter everything out that the driver does on foot. We just want the actual driving distance.
Yeah, okay.
I hope I understood the question correctly.
Yeah, and I have an answer to that. It will be possible on with the 5G. On 5G network, it will deliver also the altitudes. So in this moment, it's not so feasible. Good, thank you, Stefan. We will try to switch again to Daniel, but please, Daniel, only for 3 minutes, maybe one slide and conclusion. Don't be upset on us.
Yes.
Well, I'm afraid it's not better on my side.
No, it's not better.
About that.
Okay, so my proposal, we didn't hear you. No, it's a
Okay.
kind of problem. So we'll try one more time, but at the end of the session, if we have time. But please call on the phone. You have the phone number in the WebEx details, because I think it's a problem also with the sound. Sorry for that. Also, all the presentation will be published on our web conference site. So after this, they will kindly ask you to send the presentation, the PDF, PowerPoint, whatever, in order to be published as a PDF on the website of the conference. Okay.
Ciprian, you're muted.
Oh, sorry. Okay. Sorry. So the next presentation is a set of R packages to compute population count from mobile network data. So the presentation will be held now by Bogdan, I think. So you can share your screen.
Just a moment.
Also, this presentation is a very important one. Is from a MEIßNER project. So please, Bogdan.
Can you see my screen now?
Yes.
Yeah.
On full screen, it's okay.
Okay. Thank you very much, Ciprian. My name is Bogdan. I work for Statistics Romania, and I will present you a set of 4 packages designed to compute population count, starting from mobile phone data. These packages were developed together with our colleagues from Statistics Spain. First, few things about the context. This work was done within the MEIßNER Big Data 2 project under the work package mobile phone data. We developed a methodological framework to compute the population count starting from mobile phone data. I will not enter into mathematical details about this methodological framework, but I will kindly ask the interested participants to read the document describing the methodology that we developed. Here is the website where you can find this document. During the development of the methodological framework and the R packages, we didn't have access to real mobile phone data. So we developed simulation software. It is a C++ software, also available for free on GitHub. You have the GitHub address here on this slide. All the packages that we developed were tested using these simulated data sets. One thing I want to emphasize, using simulated data sets provides us what we call the ground truth, which means the real number of individuals in a certain geographical area. And this number allow us to assess the accuracy of our models. So here we have an overview of the R packages. We have 4 R packages. All these packages are available on GitHub. You have here the address where they can be found. So the R packages are destined. It computes the location probabilities for each mobile device. The second one is called deduplication, and it solves the device multiplicity issue. The third one, aggregation, computes a probability distribution for the number of individuals detected by the mobile network. And the last one, we call it inference, combines some auxiliary information with the number of individuals provided by aggregation in order to compute a probability distribution for the total number of individuals in the target population and the origin destination matrices. These packages closely follow the architecture of our methodological framework. I give you here again the address where this methodological framework can be consulted. We use 2 main development principles. The first one, it was the principle of modularity, which means the division of the production process into separate modules, and the principle of abstraction, which means that the interaction is made through interfaces, clearly defined interfaces, making the internals of each module independent of the rest of the modules. All our packages have reference manuals, vignettes, and examples that show how to use them. They are computationally intensive. That's why we used some parallel computing techniques. And one of them, one package, also used some C++ code to improve the execution speed. Here we have an overview of the architecture of our production software. At the base level, we have the core network producing the network event data. The data acquisition and pre-processing layer is run normally inside the MNO, which provides to, for example, to NSI, a form of simplified network event data together with other network configuration parameters. The first layer implemented in R by us is the geolocation layer. I told you that it computes the location probabilities for the mobile devices. It provides these location probabilities to the deduplication layer, which deals with the duplicity problem. The output of the deduplication layer goes up to the aggregation layer, which provides the probability distribution of the number of the individuals detected by the network. And finally, this number goes to the inference layer, which provides the population counts for the target population. You can see here that some layers in this hierarchy also take inputs not from the neighboring layer, but from other distant layers. We pass the data from one layer to another using secondary storage because these data sets are normally very large. All these packages need a map, a network inside this map, a mobile network inside this map, a set of individuals carrying 0, 1, or 2 mobile phones. We overlap on this map a rectangular grid of tiles, and we start from computing the location probability of each device for each tile in this grid at each time instant, and we end up to the population counts again for each tile of the grid. The first package in this hierarchy, this team exploits the network events data to compute the localization probability for each device and it uses for this hidden Markov model. I will not give you very much details about this package because it is the subject of the next presentation. My colleague Luis from Spain will present in a greater detail this package. We have here the inputs and the outputs of this package, the network event data, some parameters of the network, and some general parameters like the grid size, the file size, the sequence of the time instance, and it outputs two types of files, the location probabilities for each device, each tile, and each time instant, and the joint location probabilities, again, for each device, each tile, and consecutive time instance. The output of this package looks like this. We have here a sample from a location probability CSV file from a device. For each tile at each time instant, we have the location probability. The joint location probabilities show two consecutive time instants, the tile number, and the location probability. So I will present here a very short visualization. The blue point is a person carrying a mobile device. You can see how the location probability evolves over the time. The small black points are the antennas of the mobile network. The next package in the hierarchy is called deduplication, and the main purpose of this package is to classify the devices as being in one-to-one or two-to-one correspondence with its owner. We only consider that a person, an individual, can carry 0, 1, or 2 mobile devices. Generalization to more mobile devices is easy to be done. It only will increase the computational costs. This classification is a probabilistic one, which means that we assign each device a probability to belong to one of these two classes. We've implemented two approaches, a Bayesian approach based on network events and the trajectory similarity approach. The inputs of this package are the network event data. We used only a simple form of network event data, meaning the cell ID where the device is detected at each time instant. We also use here the location probabilities coming from this scheme and some network configuration parameters. And this package has a single output file, a CSV file, where we can find each device and the duplicity probability, the probability to belong to one of these two classes. Here is a sample code. Each package in our hierarchy includes some test data. So you can see here that after reading some input files, the main function of this package is called compute duplicity. The first parameter here is the name of the approach. Remember that we have two approaches. So this single function outputs the duplicity probabilities for each device. Because this package is computationally intensive, we used a parallel package to spread out the computations among the several working nodes. And we also ran a short scalability experiment. We have here in these two graphs the speed up versus the number of working nodes. And we can see that this speed up is almost linear, which means that our package scales well with the number of working nodes and devices. The third package is called the aggregation, and it provides a probability distribution of the number of individuals detected by the network. I must emphasize here that the number of devices is not the same with the number of individuals, because an individual can carry, for example, 2 devices, and we have here a problem of overestimation. Again, I will not enter into mathematical details. Only one thing, this probability distribution, after some mathematical computations, we found that it is modeled by Poisson multinomial distribution. This distribution, Poisson multinomial, it is not very simple. So we use a Monte Carlo simulation method to generate random values from this distribution. The inputs of the package, the duplicity probabilities for each device, and some general parameters, the grid and tile size, the geographical regions under consideration, the sequence of time instants. It has two outputs. One output with random variates used to compute the point estimation for the number of individuals detected by the network. And the second output is the number of individuals moving from one region to another. Giving the output as a probability distribution has two advantages. It allows us to compute any point estimation that we want, mean, median, and so on. And it also allows us to compute some uncertainty measures, like the coefficient of variance, the credible intervals, and so on. Here is an example how to use this package. Again, we read some input data. The package has two main functions. The first one, RNet event, generates random values for the number of individuals detected by the network, and the second function generates random values for the origin destination matrices. Here is a sample output for each time instant and each region. We have several random values generated from the Poisson multinomial distribution. We can compute then any point estimation that we want. The origin destination matrices are given here in the right part of the slide. Again, this package is computationally intensive. We run a scalability study. We can see here that the speed up is almost linear with the number of working nodes, which means that the package scales well. The last package in our hierarchy, the inference package, combines some auxiliary information like population registers and MNO penetration rates with the number of individuals detected by the network to provide the distribution of the target population count. We have here three elements: the observed data, the target process, and the underlying parameters. Depending how we treat these three elements, we developed three approaches to compute this probability distribution, and after some tedious mathematical computations, we found that we have three main solutions: a negative binomial distribution, a displaced beta negative binomial distribution, and a Poisson limit of the negative binomial distribution. All these three approaches model the distribution of the target population count. The inputs of the package, the posterior location probabilities, the duplicity probabilities, and the random values provided by the aggregation, together with some auxiliary information, the register-based population counts, and the MNO penetration rates for each territorial unit. The package has two outputs: the probability distribution for the target population count, given as random variates at each time instant, and the origin destination matrices. Here is a sample of the output. Below here we have the random variates for the target population count. For each region, we have a number of random values from which we can compute estimation, like here the mean, mode, median, and we also can compute some uncertainty measures like credible intervals and so forth.
Sorry, Bogdan. Can you conclude, please?
This is the last slide. This package also exposes its main functions as an HTTP REST API. This feature is implemented in the Plumber package. It allows us to process the data even if we don't have the data inside the NSI. The data resides inside the MNO premises, and we access the software via the REST API. Thank you very much.
Thank you very much, Bogdan. We have a question from Martin Libert. Thank you for the presentation. Could you please describe the data MNOs provided to NSI? Do you have the specific data structure defined for this? Will the MNOs agree to provide this data? So there are actually 3 questions.
As I told you in the beginning of my presentation, during this process, during this project, we didn't have access to real MNO data. We could see some real MNO data from a certain country in Europe, but to develop our methodological framework and our R implementation, we use simulated data. At one moment in time, we compared our simulated data with the real MNO data that we saw, and they are very, very similar. Only that the single difference is that we have only simulated data. There is no NSI, as far as we know, has a long-term access to MNO data in Europe, maybe in the future.
Okay, thank you very much, Bogdan. We have one more question for you, but I will kindly ask to answer directly through the Q&A section because we have one more presentation. So thank you again, Bogdan, for this very interesting presentation, and also for these very relevant results and good job during this project. Sorry for the delay, but I think all of you stay very attentive with this very nice presentation. We have a very nice session today. So the last presentation from today it will be delivered by Luis Zanguiaio from Statistics Spain. Geolocation of mobile devices with hidden Markov models. So, Luis, if you are ready, you are almost ready, please proceed. The floor is yours. Thank you.
Hello, can you hear me?
Yeah, we can hear you. If you maybe put the presentation on full screen.
Yes.
Thank you. Good, thank you very much. Bye.
Okay, I'm Luis Zanguiaio from the INE, the Spanish National Statistical Office. I'm going to present the STEAM package, which is part of the set of package which was already presented by Bogdan. I'm going to talk a little bit about context, but it was already presented very well. So I just want to say that the STEAM does the geolocation part of this this graph. So it's a little part of something bigger. Well, now just this thing is more or less just hidden Markov model estimation package, and there were many, and still there are many. So why write a new hidden Markov model estimation package? Well, first of all, in our case, the transition matrix is expected to be highly sparse, and this is because when you move from one position to another, you cannot, let's say, jump. There is not going to be gaps in your trajectory. So the transition matrix in our context is expected to be more or less almost diagonal. Most estimation packages are designed for dense matrices, not sparse. Still, there are some. Another reason is that, well, linear constraints are expected to hold between the coefficients of the matrix. It's both a good idea to limit the number of parameters, and also it's sometimes natural because of the maps. For example, the same road in several points would be expected to behave similar. Which is related with that testing is especially optimized for some specific kind of constraints. The equality between two transition probabilities, which is related also to isotropy. That there are places where the transition patterns are similar. We don't know any other hidden Markov model estimation package that has this characteristic. In general, we can say that it's an unusual HMM estimator because it's designed for a high number of states, but with a very, very small number of parameters. So how does it work? Well, we define a model, which is just an R object. Then we initialize that model, which just, well, updates some parameters inside the object model. We fit the model, which tunes the parameters inside the model and returns a model with optimum parameters. And finally, we can do the geolocation. The initialization finds the transition probabilities that satisfy the constraints, because depending on the constraints, it might be not so obvious. And also computes a QR decomposition to find a minimal set of parameters. Because with many constraints, the parameters needed are going to be very small. Well, we use RCPP and RCPP again to improve performance, which is very important, especially for sparse linear algebra computations on 3 matrix problem. And for likelihood optimization, we just use constraint optimization packages, just like SolMP or Donald P2, or even it's also possible to use from package stats const optim. Well, this is an example of how could be used this thing in a toy sample. Here we have 5 states, a model with 5 states. We allow transitions from 1 to 2, 2 to 3, so on, and finally 5 to 1. And also we have the constraint that the transition from 1 to 2 and 2 to 3 are equal. It's possible to add general linear constraints. It's not they are not all equalities between transitions, right? As I have said, it's just optimized for this kind of constraint. So the emissions model we can add the emissions model. We initialize the model, and this is most at random. So we have a likelihood. Well, this is in fact minus log likelihood. So the smaller the better. We fit the model and we get a smaller likelihood.
Luis, I kindly ask you to conclude. Thank you. I'm sorry for that.
Okay. We also have the rectangle model, which can be defined as this, and it just have 2 parameters. About computational efficiency, it scales well for map size in general, and even a stock computer can carry out the computations without problem. Since the number of devices are expected to be high, it becomes an inversely parallel problem. And well, also the small number of parameters makes easier the task of the optimizer. So thank you.
Thank you very much, Luis. Sorry that we are a little bit late than the schedule. So yeah, I think that it is for this session on R for web and other data. So I think we don't have at this moment more questions. Thank you again, Luis. Thank you to all presenters. And it was a very nice pleasure for me that I could chair this session, very interesting session. So, Alex, I think you can have the floor now. Thank you very much.
Thank you, Ciprian. Thank you for chairing the session. And thank you to the presenters. We are at the end of uRos 2020. It is already quite late, so I won't keep you for very long. We saw 2 keynotes, about 20 live presentations, and 8 pre-recorded presentations. Do not forget about them and watch them on our YouTube channel. If you missed some of the presentations, you can still watch the recording on YouTube. All of them should be there soon. A big thank you to all the presenters and everyone involved in organizing the event and sharing sessions, of course. We are aware that not everything went perfectly smooth, but we are quite new to the virtual event business. If there will be a repetition of this kind of event, we will take the lessons learned on board and hopefully improve. Everyone will receive a feedback questionnaire next week. Please respond to it. It will be valuable information for us to improve in the future. So what's next? If you have ideas for keynote speakers we should invite, or for formats for sessions we should try out, just get in contact with us. The good news is there definitely will be a number 9 for this conference. So uRos2020 will happen. At the moment, it has not been decided if it will be a virtual event or a physical event. This will be mostly decided by the circumstances in the ongoing pandemic you are probably all well aware of. The time frame is autumn 2021. Most probably it will be September. And the location for a physical meeting would be in Bucharest. But if any other NSI or organization is interested to host this event next year or following year, please contact us. We will take that into account, and we would also be happy to move uRos around a bit, of course. So currently we want to decide on uRos2021 details next spring, so spring 2021. Yeah, with this, I wish all of you good health, all the best, happy holidays, a good time in the remaining of 2020, and all the best for 2021. See you all in 2021, virtual or in live. Thank you.
Thank you, Alex. Thank you, Statistic Austria, and thank you all the presenters.
Thank you, Alex, for your great organization, and I thank you for all the organizers, also to the keynote speakers and all colleagues around the world for this great conference. Thank you again, and happy holidays.
Thank you. Bye-bye.